Welcome back, everybody. We just took our midterm. I will be grading that soon, so I didn't look at it. Over the weekend, I left them on my desk, and I was happy that they were there, and I didn't take them home. I'll take them home this week, and I'll get through them. I know a lot of people are panicked, and oh no, what's new? So, hey, I understand. There's ample opportunity to implement things for extra credit. If you have a bad day, I'm sure you can recover from it in the future. We will have a final that's going to be a take-home version of the final. I'll send out a bunch of questions, give you a limited amount of time, and say come back to me in the next 5 hours or so, something like that. It's going to be the format. And so I understand probably right now a lot of you haven't taken an in-class midterm for a long time. And that was a 50-minute midterm, so there are a lot of reasons why you might be a little off your stride. So again, the whole goal of this class is to learn Bayes, to be able to understand theoretically what's happening implementation-wise, how to do this stuff. And there's lots of other Bayesian classes as well. This isn't the end-all, be-all. This is just kind of a survey of all the things that Bayesians really do. And after you get this stuff, what we do with it is pretty radical, I would say. What we put distributions on. The Bayesian format is pretty flexible, but there's a lot of technicality in the mathematics. What's happening, the asymptotics also kicks in. We'll be studying that when we get here to testing. So, just a quick announcement. Homework 4 is out. I'll go over that with you in just a moment. A lot of it is implement the things that we've already done. Don't forget to add in the Wishart carryover from homework 3. So there were a couple problems. You'll be redoing one of them and writing it down for this homework, so it's already built in. But there was a problem about integrating across the Wishart matrix. And that one I want to be included in this homework. Sierra will remind you guys on Slack what that problem looks like. And I gave you a few pointers and hints in a previous lecture on how to solve that problem. We'll be doing review this Thursday as well. And the next homework will be due, I made it due on a Monday. Again, I know I said I'm going to aim for Friday. But there's a lot of implementation in this homework. And so you don't need the time if you wait that long. So you guys know how it is. It's either a 15-minute exercise or a 15-hour exercise. And for people that spend 15 minutes, it's because they spent 15 hours many times getting technique in their implementation, understanding what they're doing. I would never implement anything unless I understood what it was I was implementing and why it should work and what it all means. So in some of the extra credit that people have handed back to me, it's kind of clear that either there's a fundamental gap in like what you're implementing or I think it's that. You start to code something up and you don't know what it's supposed to be doing. So we'll be spending a little bit more time on MCMC in the next couple weeks. I also want to integrate in some testing into all of this. So what I mean by testing is hypothesis testing. So typically this thing. And nobody has any gripes about this, completely uncontroversial. Everybody totally agrees on how to do testing, right? Absolutely not. So this is the stuff everybody disagrees on. I want to show you what a Bayesian does, and then I want to build into this class where we can make it useful. So, and where testing can be really useful is in model selection, those sort of principles. So how close to 0 do you need to be before you throw a parameter out of your model? Something like that. And that's been a fundamental problem for a long time. So back in my college days, people did things like ridge regression and lasso, pretty easy. There's some implications to doing that. And this whole question of how you sparsify a model has gotten more dramatic since when I was in college, because now there's many more parameters in models. I want to teach you that this problem is hard. It is unclear what the answers are sometimes, but you can get a semblance of an answer. So when we're selecting models, what are we doing? It depends on who you ask. Are we searching for the truth, which this problem confronts, hypothesis testing, and we're trying to eliminate truths and narrow in on truths? Is that what we really do? Hopefully asymptotically, but I will try to teach you during this, because there's a hot debate with the counterpart to that, that is the p-values. So we'll be covering p-values as well when we talk about all of this. People sometimes use p-values for their model selection, and sometimes you can get semblances of answers that are okay and they work all right. But maybe there's improvements and things we really need to consider when we say something is a 0 or something like that. So hypothesis testing, I'm going to interweave this, and then we're going to do kind of a hybrid thing where we do a lot of Mcmc for doing model selection. It's going to have a lot of theory baked into it. I think that's good Bayesians are doing that all the time. They have good theory baked into their codes. They know what should work, and they're making adaptations all the time. And so then there's a couple things to think about. Are your inferences great? Can they be improved? And can your code be improved? So can you make it faster? So there's two things people are always trying to do. Usually making things better means more complexity. Usually means longer running time. And so where do you make your approximations? What's reasonable? So we'll study this problem from a couple different perspectives. I say we're going to cover theory, but we'll also, after we go through a lecture or two that are theoretical, we'll go into implementation issues. And these are big issues. A lot of people have asked me in my code, why do I do certain things? And some of you guys have a fundamental misunderstanding as to what I'm doing. I haven't changed the algorithm any, but maybe it doesn't appear the way you think it should have. And I'll be addressing that as to why I implemented it the way that I implemented it. Lots of issues. I like people to see all the numerical issues. They can kind of arrive. So when you do this on a chalkboard and you do it on a computer, there are things that you will notice are different. So dividing by epsilon is no big deal on the chalkboard. And I can take epsilon and think about it in a limit and do all kinds of things that I understand mathematically should happen. On a computer, it's all very different. And so all of a sudden you get an imp in the middle of your code or a man, and the whole thing just goes berserk. It's not supposed to do that. So our theory tells us it's supposed to work. So I want us to understand, why does the Metropolis-Hastings algorithm work in the first place? I'll almost tell you the whole story. So we need a little bit more on Markov chains to understand the complete story. And so I'll show you just the part I'm about to stop short at. I'll give you an illustration of it. Any questions before we jump into all of this? Maybe just a touch on homework 4. We'll look at that and then we'll jump back to the MCMC. Okay. I kind of like MCMC theory because it's kind of implementation and theory at the same time. You can do something with it. So it's kind of the best of both worlds. Sierra can tell you, when we design algorithms, we are thinking about the theory when we design them. So the properties that we need out of our proposals. What does the reverse proposal look like? That's a big question. Okay, let me switch gears just real quick. Problem should look familiar, the rat problem. So I just have written it down. So if you're thinking, oh boy, there's a lot to think about right here, this is exactly the same problem that you're supposed to work out full conditionals for. One of these full conditionals is the carryover from last time. I want you to just write down what those full conditionals are. for everything, and then I want you to implement everything. I want you to implement the give sampler. So at the very bottom it says, in previous homeworks, you wrote down the whole conditional distributions. You haven't probably done it for the Wishart, but it's as easy as all the other ones. And then I want you to implement that give sampler, and I want you to compare it to the results in Gilpin and Smith. There is discussion in the paper as to how they parameterize or how they hyperparameterize their priors. And so my recommendation, if you wanted to make it easy, is go to the paper and see how they did it. And if they're on a different scale, like Wishart versus inverse Wishart, you just go to your tables and you convert real quickly to however you want to implement it. It's up to you though. It's arbitrary in terms of its choices. If you want to transform back to their scale, so say you're working on the precision scale and they're working on the covariance scale of everything, and you want to do the transformation, all you have to do is each matrix that you get out of the simulation, you just invert it. So, and that will take care of everything. No Jacobian required because it's a discrete sample from something. So on a computer, there's no such thing as a continuum. Just do the transformation automatically. And you should be able to compare everything to it. If you don't want to be so diligent as that, that's okay. So if you want to use the reference forms of the priors, that'll make your life probably easier. And some of the inputting a little bit easier for you. Just make sure you compare to their answers and show how they are similar or different. I suspect, because the data set is relatively small, your priors can have a decent amount of influence. And obviously they have subjective input from their scientists, why they plug stuff in as their hyperparameters. For instance, they'll say, well, on average, scientists believe this is true. And so they'll calibrate the expectation of their prior distribution with that. I think that's fair game. So again, the real question in this whole problem is there covariance between the weight parameters in the RAP example? So you'll implement that. This is all on the web page right now, and there is the data set inputted for you already, and there's a text file as well. I think the data set looks like this. There it is. There's 30 racks. I didn't really put in that header, so sorry about that. You're going to chop it out anyway. So 30 racks, and those are the 30 time points, 5 racks, and their weights vary through time. So pretty clean looking data set. I gotta say, I never get to see these anymore. So I haven't seen these in like a decade. So then somebody's like, here you go, and there's no weirdness. Like, my notes have missing stuff in it, all kinds of weird stuff, fallout from experiments. And so that's where statisticians get to be really useful, is when they're dealing with all these confounding issues and deconfounding everything in the model. Anyway, this should be fun, so implement that. It's not a lot of code, because everything is conjugate. So you just have to write down the right give sampler. So you gotta make sure your full conditionals are right, or it won't work. When we get to implementation issues, I'll try to help you to diagnose code problems, like things that you can use. But at the end of the day, it's all a lot of work. You sit there, you be diligent, and you know what to check. You know how to systematically go through your code and check what's working and what's not working. And so that's the beauty of it all, is it makes you slow down. So, and that's true for all of us. So try to develop good technique as you go through this. I used to have to apologize for this stuff 10, 15, 14 years ago when I started. But nowadays, we gotta know how to do all this. Okay. So now you gotta know how to do math and computing. So that's the trade for all the technology that we get access to. Same thing for problem 2. This is that same regression problem. So you'll simulate a cloud of data. It's going to be Cauchy. It's going to look like an ellipse and turn. And so you've simulated that already. Now I want you to implement the give sampler for everything. So you've written down the full conditionals. You'll have all your full conditionals for the gammas. You'll have your full conditionals for the betas and the phi. I want you to fit that regression line to everything. So you fit the wrong regression line to it, but it gets steered by your outliers. And let's see how the regression line looks under this give sampling thing. It's really weighted least squares, but we're integrating out the weights is what's happening in give sampling. So while there's some math written down here, all you're doing is you're implementing these 3 steps. Boom, boom, boom. And how does the integration take place? Well, I only just look at the betas and I don't look at phi or the gammas. Those are now integrated out in space. So it's kind of cool. We will get into testing soon. I've got this problem right here that's kind of interesting because usually we give you the true model. We have you simulate something, true model, do something, and pick the true model. This problem is a little bit different, where I'm going to have you simulate from a mixture model. And maybe Sierra will give us a lecture on mixture models, or maybe I will. We'll negotiate it. I know she's got a good sequence of lectures, and she has one online already for you. Maybe we'll point to that, and I'll try to emulate how well she did in that lecture series. We're going to simulate from the wrong model. So here I've written down xi's are normally distributed, but I'm going to let the betas, the mean parameter, change. So I want 400 of those xi's to come from mean 10, 200 to come from mean 15, so on and so forth. And what we'll do in this problem is we will look at this hypothesis. So h naught theta is equal to 10. So we'll have our stuff that was generated from a mixture of models, 4 different models with varying degrees of weight on them. That's proportional to the sample size. And see what happens if we ask a question that's not true. We said, hey, did these x's come from a model where theta is equal to 10? The answer is no. It did not, because it came from a model with other stuff. And I want you to compare the Bayesian procedure and the p-value calculation for each one of these hypotheses. So in the case where you are only testing wrong models, what happens? And I think in this problem, for the amount of data points that we have, all the p-values are absolutely small on all these different hypotheses. It's theta 10, 15, 17, or 20. And the p-values say it's none of those. And so the p-values win the argument. Nope, 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 nope. The Bayesian, what they're going to do is they're going to compare all these hypotheses to each other. And what the Bayesian's ultimately going to do is going to say, well, out of all of your model assumptions, these one component model assumptions, it's going to compare which one looks best out of the whole universe of hypotheses. And they'll come up with very different answers, and I kind of like that because it highlights at least where p-values are aiming, what they do right. Unfortunately, not everything's a simulation in the world, and there's probably a different question that we should be asking in the first place. So later on, I'm going to teach you how to do mixture modeling using give sampling. And so we'll build this into a future homework where you'll be give sampling and getting the answer to the question right, where we don't ask the wrong question in the first place. So what's the wrong question? Is theta equal to 10? No. And that's the answer in all modeling applications. Is theta equal to 10? No. Or whatever your hypothesis, theta is equal to theta naught. Answer, in a real setting, no, it's not. So really, in reality, we're always fitting the wrong model. And that's where there's a problem with the application of p-values. We can come up with answers as Bayesians, but they might not be good too, depending on how we do our modeling, if we have the right model class to even work with. So lots to discuss in terms of hypothesis testing and all of that. You don't have the skills yet to do this full problem, but you can definitely do the p-value calculation, I'm sure. And then I have you do a few theoretical problems. We'll be talking about Bayes factors soon. You won't know how to do this. You might know how to do problem 5. Prove that under the null hypothesis, a p-value is uniformly distributed. If you don't know what a p-value is, look it up. This is true. This is in any book. We'll go through that proof. I might give you 2 different variants of that proof. The proof that I like and the one that appears in all books. What I really always want to know is how's the p-value distributed under the alternative hypothesis. And that's a calculation that sometimes people do. I think people should do it quite often because nulls are rarely true in reality. Okay. Let's move on to Mcmc theory. I'll come back to this in a second. I want to tell you a few things and get us motivated. So let's just recall the Metropolis-Hastings algorithm. Get some notation. Call the Metropolis-Hastings algorithm. Probably let's state the goal of the algorithm first and then tell you how the algorithm accomplishes the goal. So our goal is to sample from some distribution. So sample from some posterior distribution. So all this is supposed to mean to you is a posterior or some distribution right here. So what do I mean when I say sample? I mean that we get these theta i's coming from this distribution. And I'm able to do it a whole bunch of times. So this thing right here is proportional to likelihood times prior. Bayesians are always sampling from some distribution. This is a general purpose algorithm. You give me some functional form of what the curve looks like, and this algorithm will sample from underneath that curve. Higher values, it will be grabbing more often theta's in there. So just as a quick illustration, pi theta, I'll think of it as continuous for most of my discussion here. Looks like this. So this is a function of theta. And what I mean is that I'm going to grab samples in this region right here. So this is my region R. And I'm going to grab them with probability proportional to the area under that curve. And so the frequency of samples from R is proportional to integral in R pi theta given x over theta. So I'm just going to integrate over R. And my samples are going to happen proportional to this. So if I grab 1,000 samples, I want to multiply my 1,000 samples by this number. If I integrate it over the whole posterior, that's 1. So I'm assuming this is all normalized. It's just a concept to us right now. And when I integrate over just region R, they look the same. that's a number between 0 and 1. So it's a probability. And so if I have 1,000 samples, then I want on average that 1,000 times that probability, those samples live in this region right here. And I can do that by sliding this region anywhere I want. And any algorithm that gives me that is an effective sample. So it works very well. The Metropolis-Hastings algorithm does this through these 3 steps. 2 of these steps get iterated over and over and over again. So Metropolis-Hastings is going to first initialize everything. So theta 0 is equal to some initial value. I'll just write it down like this. Some initial value. It's an iterative algorithm, you got to start somewhere. So it's probably not necessarily even in the stationary region. If it was, your sampler is probably going to run pretty quickly. If this is far from where this posterior mass is, let's say theta 0 is way out here, then it's going to take a long time to come over here, depending on your proposal structure. So we initialize. This doesn't have to be one-dimensional, and it doesn't have to be continuous for the purposes of this lecture. If it's discrete, we'll change all our densities to probabilities. If it's continuous, we'll move them all to densities. If theta is high dimensional and some of that stuff is discrete, countable, or and some of it is continuous, as long as you've placed your measure properly, i.e. probabilities on the discrete stuff, the countable stuff, and densities on the continuous stuff, we're all in business. So this can mean quite a lot of things to you, this pi theta. So without any loss of generality, I think you can think about it as continuous and one-dimensional, but everything extends. What we're going to do is we're going to run this algorithm for some large amount of time. Some large amount. And we're starting to get a handle on what's big. So, well, everything needs to converge. And we've kind of seen that in practice through a bunch of examples. There's 2 steps that we just bounce between. So all MCMC is really about this. So theta star, my proposal, is going to, my proposed value is going to come from some distribution. I'm going to call it theta right here. I'm going to be a little bit more general. I know in previous lectures, I just wrote down theta sometimes. But this is a Markov algorithm. And so, since it's Markovian, I can preserve all Markovian properties of this algorithm so long as I just let my proposal be Markovian. So I can either just propose independently, I got something that covers this very nicely, or in previous homeworks, we've made this a random walk. And so this can be conditioned on where we were last time. You can either have that conditioning there or not there. The whole question in MCMC is, what is this proposal function? So our random walk kind of got centered where we were last time. And that's a good strategy if you're in a fairly connected space, that you can walk from the high probability regions from one to the other. If you can't do that and they're disconnected, a local strategy is going to fail. So basically you're going to be walking off into the abyss all the time into the low probability areas, and you won't know how to bridge everything. We'll have greater discussion about this, but this is the whole question. How do you pick a good proposal? In the previous homework, you got to have fun with this question a little bit. And there's a good write-up online that gives you all the answers to all those questions. So if you didn't know this yet, the answer to how do you come up with a proposal is all in Darren Wilkinson's write-up. It's on our webpage. And there's a couple of things that he advocates. Okay, so I'm going to be a little bit more specific, and I'm going to say, I'm going to consider a transition. I'm just going to say that my acceptance rate is dependent on these two values right here. So I'm just going to use this alpha right here. This is just going to denote an acceptance probability. So the nature of the algorithm is to propose something. You're in a current location, you propose something else, and you're either going to move to the proposed location or you're going to stay where you are. So those are the two possibilities. And this acceptance probability is computed is the minimum between 1 and the ratio of our target evaluated at the proposed location compared to where we were last time. I'm just going to make this a T and explain that in a moment. This will be the acceptance probability of transitioning to the next thing. This is my probability regardless of anything. We finish writing out this quantity right here, that this is going to be G theta star given theta T minus 1, G theta T minus 1, theta star. So I always say this is the ratio of targets. And this is the inverse ratio of proposals. So just to be clear, these are density functions if we're thinking about this as all continuous stuff. The nice bit about this is if we are in our Bayesian setup, we don't need to normalize that distribution. Everything would cancel out in that ratio. That's just a constant regardless of where I move theta to. So you can plug in likelihood times profit. Inverse ratio of proposals, basically we got to make sure that we can move back to where we proposed from is what we're thinking about. So final thing is just to use this acceptance probability accordingly. So theta T is going to be equal to either theta star or theta T minus 1. This happens with prob alpha theta T, alpha theta T minus 1. This happens with probability 1 minus alpha theta T given theta T minus 1. I take it back. I would rather this just be the star. I think it feels better for me. It's all very arbitrary. I think it conveys a better point if it's the star. I don't like computing things, having arguments that don't live on the right-hand side, that live on the left-hand side. So aesthetically, that's very puzzling to me. But this is what you do. So you flip a coin at the end of the day. So this is just a Bernoulli coin flip. And in my code, I have that all implemented on the logarithmic scale. So I'll tell you more about that when we dive under the hood. So that's Metropolis-Hastings in a nutshell. 2 steps that are just repeated. I want to think about this concept really quickly, the transition probability. I'm going to call this the transition rate. So if we're dealing with countable stuff, random variables. This is a probability. If continuous, it's a density. And we have got flexibility to be dealing with both simultaneously. And that's why I call this a rate. Okay. So you like to think of it as just a one-dimensional thing that we're talking about. That won't hinder your knowledge of all the theory. Just say, automatically do induction, grow this thing into other types of random variables and higher dimensional stuff. Okay, the transition rate I'm going to denote is rho theta t given theta t minus 1. So in my continuous example, this would represent the density function for transitioning between theta t minus 1 and theta t. I can't call that a probability in continuous length because the probability of moving from anywhere to anywhere is 0, but stuff happens anyway. So it just means it's so vacuous compared to everything else, something has to happen. So if I were dealing with discrete random variables, I'd be calling this a transition probability. And this would be something, if it were all very countable and finite, I could put it into a matrix and build the Markov chain like we're used to thinking about. I'm going to write it down continuously, though, just so that we can extend our way of thinking about this. My question is what is the transition rate for the Metropolis-Hastings process? I'm going to say this is for Metropolis-Hastings. So any Markov process will have this. I want to talk about the specific one that's specific to my algorithm. You can't really answer the question until you look at the algorithm. So you need to be staring at the algorithm to even answer this question. But what we kind of notice in this problem is regardless of this being continuous, this part's discrete. So there's a continuous part of this, and there's a discrete part of this. So flip this Bernoulli. And so that's another reason why we call it a rate. That even in continuous land, there's this probability that pops up. So these two things happen, and that is our rate. They're conditionally independent of each other. I do this one first, and then conditional on this, I do this one. So they follow in sequence like that. So they're not independent of each other, but they're conditionally independent of each other. So I need to have theta star from this step before I can do this step, step 2. So I consider this whole thing step 2 right here. Compute the acceptance probability. This is what I call the Metropolis-Hastings decision rule. And then I just flip this coin once I have this probability. So 2 stochastic elements. So how do I figure out what this total rate is? I multiply them together. And that's all there is to it. So this is equal to alpha and this is where the notation gets kind of funnier because I put that little star in there. It would feel better if I had the theta t. So if you want to know what I was thinking about, that's it. So if I want to move from theta t minus 1, I can be more specific right here and say, let's move to theta star, the value we just proposed. So this is my proposed value. I think we've worked out the kink on the notation right here. Let's just throw a star right there. So what is this? This is going to be theta star given theta t minus 1. This is going to be times how I even got that theta star in the first place. So, theta star. theta t minus 1. So I'm just multiplying these things together. This is really just step 1 right here. This is a density of transitioning, and this is a probability, step 2 in the algorithm. Those are those two things that I've done. And so what's the total rate product? If theta were a discrete element, then this would just all be a probability. And you would have computed it the way that you know how to. So that's all you're doing. You're transcribing the algorithm into this mathematical form. So in a nutshell, this is Metropolis-Hastings. And basically, I'm just moving through this probability right here. I want to ask you to think about real quickly, what is rho theta t minus 1 given theta star? And this is the reverse transition. Now, this is harder for us to think about, what the reverse transition is, because we only run the algorithm in one direction. But it's basically, if you ran the algorithm in the reverse direction, what would it look like? If this is a time-reversible algorithm, so note, and here's a technical thing that's important, that this is the part that we're not going to spend a lot of time on. Everything else I'm going to tell you about. So we need a little bit more on Markup chain theory to really understand this, time-reversible Markup chains, but I encourage you to look it up. But this is the part I'm going to kick under the rug in this class. Note, if the process is time-reversible, and I'll just be a little bit more technical in my notation. I only choose the same letter, but these are different processes possibly in a Markov setup. And so if you run the chain forward or backward, do they have different properties? And sometimes the answer is yes. What I'm going to tell us about Metropolis-Hastings is the answer is no. It's time reversible. But if these two row functions are the same functions, then this is a time-reversible Markup chain. And I think that the language makes that fairly intuitive. They're the same processes governing the different directions that you move. So if rho theta star given theta t minus 1 is equal to rho r theta star theta t minus 1. If they're the same processes right here, then this is saying that in the reverse direction, transitioning from this element, which is the same as this element, has the exact same properties. Okay? So if the process is time reversible, then essentially this is equal to this. These are the same functional forms, is what I'm saying. If I can switch these arguments around in the function, then I would say the process is symmetric and time reversible. So I'm not saying necessarily that it's a symmetric process right here. So I don't want to talk about this. We'll have to deal with more mathematics if we do. Let me show you a picture, however, that we're pretty familiar with. We've run our Metropolis process. I kind of have a Metropolized version of Gibbs in everything. The very clever student will recognize that Gibbs itself is not time reversible, but only in a very trivial sense. Let's forget I said that. But we've looked at this. Let's forget I said that for now. We've looked at this process where it's converging. It started somewhere over here and walked around this boundary and finally collided into the posterior distribution. And from that, I have these margins that I can look at. The question is if I zoom in right here into everything, this is the distribution that it's converging to. I think I've got everything is burned in. This is the distribution that it's converging to. You'll notice that the red line is actually in the tail of the distribution. I ran it like 18 times this morning until I got a red line that was not in the middle of the distribution. Because somebody came up to me and said, I don't always get it in the middle and I don't know what's wrong with my code. And that's the nature of statistics. Sometimes you're in the tails. You're supposed to be every once in a while. And so if your thing is well calibrated, frequent tests like that, 1 out of every 20 times you're going to be in those 5% regions. If I zoom in right there and I look at this distribution and I think about it moving from left to right, I might ask myself, well, if I moved from right to left, do the patterns seem the same? The way it goes up after it goes down. And so is there any weird deviation in there depending on which direction I'm scanning my eyes? Are the patterns the same? And I would say, looking at this with my very well-trained eyes, yeah. So, but if I backed out a little bit, and I looked early in the distribution, I can see that there is a pattern that it depends on which way I scan over this. It makes a big difference. So if I'm moving from left to right up to that burn-in period, it looks like everything is drifting up. And if I go the other direction, it looks like everything is drifting down. And so the process is not reversible in that non-stationary portion of the chain. And so this illustration helps us to understand what time reversibility means. So when I'm up here, over this part of everything looks time reversible. Over here, everything is not time reversible. So as the algorithm converges, everything is time reversible. And that's what time reversible means. So we can see it just from the output of our stuff right here. Same thing happens in this margin as well. So I'll let you go play around with it. One way that you can see is it time reversible. I like to do this. Sierra will do this with some of her output. Is sometimes I'll take samples and I'll flip them around for people. And I'll bury them right into the middle of a section of everything. And I'll see if they can tell. And so, and always I find out they can't tell because everything is time reversible. So we're going to, in our proof of everything, we're going to exploit that the process is time reversible as it converges. So that's what we're trying to do. So this is the formula that we're going to start off with next time. We're going to talk about detailed balance. Detailed balance.
It's a black screen.
Yeah. Sorry about that.
There you go.
Detailed balance is just this equation. Rho, and I'm going to take off the time indices for a moment so that we're not thinking about the reversibility of everything. So I'm just going to talk about two different states. So consider two elements, theta prime and theta, well, I'll just say theta prime and theta. And they're both an element of, they both live in our big grand theta space. So I'd have to go back here and tell you where theta lives. So theta lives in this space. These are going to be elements of that space. So I want to start out with this equation next time. Theta pi theta is equal to, just be consistent, theta given a prime. And this is an equation we're used to seeing. If everything was a probability function and somebody showed this to you, you would say, yeah, I agree. So if everything was a probability or a density. And it really is that simple. So this is just conditionals multiplied by a margin. Sometimes I call this the margin of the distribution. I've been calling it that for quite some time. It would be the margin of this conditional distribution that we're playing around with. But in our case, we're going to call that the stationary distribution. And it is the margin. And we've talked about that a little bit before. The limiting thing, it converges to something. It limits to something. What is it limiting to? The margin, irrespective of your starting point. So language that we've used before applies here. And the only thing that's different about this equation versus what you would see in a basic probability class is the time aspect of everything. And so we'd have to see if those two functions were the same. Upon convergence of your Metropolis-Hastings algorithm, they're the same. So, and that's what we'll invoke. So what I'm going to show you is that this equation is true for this algorithm. And the margin for the stationary distribution is going to be that function. And so this is the algorithm. And this is our target right here. So I'm going to show you at the end that when I run this algorithm with these inputs, the margin or the stationary distribution will be this. So we'll come back next time. So this thing will be our actual target that we're looking for. And that's what we'll be sampling from. So a lot to chew on right now, but the mathematics is almost like mathematics you're completely familiar with, minus the time aspect of this. I'll see you next time. Get started on that homework also. So it'll take you a little while. Thank you.